to the thematic session of optimization in the frame of CIMAC, International Symposium on Mathematic Methods Applied to Sciences. Today with the special workshop dedicated to the 70th anniversary of Professor Alexander Khludnev. And today we have Professor Hiromichi Itou. Professor Hiromichi Itou is actually full professor in the Department of Mathematics at the Tokyo University of Science. He is a representative member of the Japan Society for Industrial and Applied Mathematics, JSIAM. His research interests lie in the areas of fracture mechanics, singular integral equations, analysis of singularities, of corner and crack, theory of elasticity, inverse problems, and others. Professor Itou, they are all yours. Thank you very much for joining us.
Okay. 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 Can you see my slide? It's okay.
That's right. We can.
Okay. Okay. Thank you very much for Mr. Chairman for introducing me. First of all, it's my pleasure to have an opportunity to give a talk in this symposium, and also then this very important occasion to celebrate the 70th birthday of Professor Khludnev. So Professor Khludnev, please take good care of your health, and I want to continue good relationship with you for years to come. So anyway, in today's talk, I'd like to make a remark on dynamic friction problem in linearized elastic body with cracks like this title. And this research is a joint project with Professor Kashiwabara in the University of Tokyo in Japan. Okay, so let's start with motivation of this research. Friction problems are very important issues and appearing a lot of phenomena occurring around us. Especially in material sciences, it's recognized discipline as tribology. Maybe one pioneer of tribology is Leonardo da Vinci, who discovered the classical law of friction in many years ago, 1493. And after that, Amontons and Coulomb established classical laws of friction. But there are just an empirical laws, so it's going on modification even now. And maybe one of the most important application is fault ruptures in earthquakes, which is typical frictional problems. Fracture occurs between two plates under huge pressure. Of course, it's very complicated phenomenon. There are some models of described as such phenomena, but mathematical analysis is very hard because of the complexity of conditions of rupture phases. So today we will discuss a very simple mathematical model. So maybe this is a very incomplete list of the references of friction problem in mathematics. I think there are not many literatures in mathematics about friction problem. Today I will talk about the result in number 1, recently published in Mathematical Notes of NAFU. And in books number 2 and 6, dynamic friction problems are treated mathematically based on variational method. Number 3 is very nice book by Professor Khludnev and Dr. Kovchnenko. Is for mathematical analysis of cracks and contact problems, and also number 4 and 5 deal with static frictional problems. Okay, so next, let's move to the problem formulation and the main result. Let capital omega be a bounded domain in R3 with ellipsis boundary. We suppose the capital omega is isotropic, homogeneous, linearized elasticity. And the outer boundary of omega consists of two parts, two disjoint parts, gamma sub n and gamma sub d, like this figure. This part is gamma sub d, and this part is gamma sub n. This is just bounded domain omega. And let gamma be a two-dimensional oriented open manifold that splits omega into two ellipsis domains, omega plus and omega minus. This dot lines is gamma. And small n and tau are normal and tangential unit vector to the round omega plus and round omega minus, respectively. And crack, denoted by gamma sub c, is an open subset of gamma. This is gamma sub c, described as a crack. And in this study, we treat only the case of a fixed crack without propagation. The two crack faces can be distinguished as the corresponding parts of round omega plus and omega minus. And set omega sub c is omega set minus of gamma sub c, the closure of gamma sub c. This is called the cracked domain. And the boundary of omega sub c consists of three parts, like this. And for fixed final time, capital T, the time space cylinder is denoted by Q sub c t, like this. This is considering domain. And next, we introduce the linearized elastodynamic equations for the displacement vector U, defined by this. This is, they have three components. And this is a system of second order linear hyperbolic partial differential equations where the rho is the positive density, this is constant, and F is the body force. And lambda and mu are lambda constants satisfying these conditions. And we denote the linearized strain tensor by epsilon, defined by this form. And we denote the stress tensor by sigma, given by the Fuchs law, like this. Here we formulate the initial boundary value problem called capital E. For given surface traction, capital F on gamma sub n, and the frictional force acting on crack, G, is in this is in this form with capital F sub n and frictional coefficient calligraphic F. This is a positive constant. And for given initial states U sub 0 and U sub 0 dot, then our problem is to find the displacement vector U satisfying the following problem, capital E. The first equation is the linearized elastodynamic equation previously mentioned. Second is Dirichlet boundary conditions on gamma sub D, and on gamma sub n, surface traction F is loaded. And on the crack, normal components of the traction vector is given by capital F sub n. And this condition is so-called the frictional condition, but the friction force G is given by this form. And the last line is initial conditions. U sub U of 0x is U sub 0, and U prime of 0x is U dot sub L. So we denote the prime is time derivative. And here and hereafter, we use notation double brackets denote the jump of the quantity between the upper face and lower face of the crack, like this one. And we denote the normal components of the displacement vector by U sub n, defined by this. A normal component of the traction vector is by sigma sub n, like this. And similarly, the tangential components is given by this form. Note here that on the crack, only frictional condition is imposed. We don't require any contact conditions, just a frictional condition. So next, we derive the variation formulation of the problem capital E. Firstly, I introduce some notations. Function spaces capital B is given by this set, and capital H is just L2 of omega sub C, equipped with the inner product denoted by this one. And the parenthesis sub gamma sub n and gamma sub c is described as the duality between the Lyon's magnet space H sub 0, 0, 1 half on gamma sub n or gamma sub c and its dual space. And this space is defined by this one and characterized by the following statement. That is the zero extension of the function from gamma sub c to gamma minus gamma sub c bar, zero extension is belongs to h1 half of gamma. And next, let small a of ub be a bilinear continuous symmetric form. That is, for orbital u and b in H, A is defined as this form. The column expressed as a scalar product of tensors. And it follows from the Cohn's inequality that there exists a positive constant C sub k such that this inequality holds for orbital u in B. Then we arrive at the following weak formulation of the problem, capital E. Assume that the initial states u sub 0 and u sub 0 dot belongs in B, and the body force F in H1 of 0th. This means the H1 for the time variable and for spatial variable, so it's L2 functions. And capital F is frictional surface load on gamma sub n. It belongs to in H2 of L2, and frictional force Fn and G belongs to H2 L2. Then, so our problem is to find U satisfying in this class and satisfying for orbital B in B and almost everywhere time t, the following variation inequality holds, so-called number 1. And also initial conditions, u sub 0x equal to u sub 0 and u prime of 0x equals u dot sub 0. And where the right-hand side of 1 is given by this form, determined from the data. As a remark, the problem E is in the initial value formulation is equivalent to the weak formulation E prime if all functions are smooth. Next, I make some comments on. I make some remarks on this problem. So reference number 2 deals with Toresca friction problem, that is similar problems to our problem, but without cracks. So in number 2, so frictional condition is imposed on the outer boundary, not crack problem. And therefore, so one can say that today's problem is the extension of the result to the crack problems. And moreover, the number 2 shows the unique existence of a solution in the case that the frictional force does not depend on T. In fact, this is an unnecessary assumption due to some certain mistakes. So we correct these mistakes, and our problem it's possible that friction force can depend on both of partial spatial variable x and time variable t. Then our main result is as follows. So assume the compatibility condition at t equals to 0, or like this one, called number 2. So this is compatibility conditions for the initial states u sub 0 and u sub 0 dot. Then there exists a unique solution of the problem E prime in this class. This is our main result. Next, I make some comments on this theorem. Firstly, the fourth line of compatibility condition, this one, is stronger than just requiring that u sub 0 and u sub 0 dot satisfy the friction condition. We don't know whether this condition can be relaxed or not. But in our analysis, so it's necessary. Secondly, for linear wave equation, the commonly used solution class of the weak solution is like this one. So, however, this class is not good for this problem because in our problem, we should take the trace of u prime. So just L2 is not enough. So we require more higher regularity of the class. So in order to do that, so we require the higher regularity of the data functions like this one. And thirdly, the following characterization of H1 of omega c is required when constructing the Galerkin approximation, which is particularly separable as a closed subspace of H1 of omega plus times H1 of omega minus. And in remaining time, I'd like to mention the outline of the proof. So maybe the way of the proof itself is a standard way, I think. So we briefly mentioned the outline of the proof. As a first step, consider regularized problem. So introduce the Sheets function phi of epsilon for positive epsilon, and like this. Then, maybe 5 minutes. Okay, so and
you
then,
remain 10 minutes left.
10 minutes.
Don't
okay,
worry.
thank you.
Yeah.
Okay, thank you. Then
5 minutes. 5 minutes
okay.
left and 5 minutes for questions.
Oh, okay, thank you. Then the variation inequality can be reduced to the following regularized variational inequality. So non-differential term appear here and here, regularized by the function phi of epsilon, like this. And because phi epsilon is a smooth function, so this inequality is equivalent to the following equations. So we solved this equation. As a second step, we consider Galerkin approximation to solve these equations. Since V is separable, recall remark 3, there exist countable members W sub 1, W sub 2 in B, which are the linearly independent of each other, such that this condition holds. We assume that U sub 0 and U sub 0 dot are in B sub M. Otherwise, U sub 0 and U dot sub 0 should be added to the members W sub K. And then for fixed positive integer M, find the approximate solution U sub N in this form, satisfying the system of ODEs and the initial conditions, like this. So by the standard theory of finite dimensional system of ordinary differential equations, we obtain the unique solution of number 5. And then so we construct the approximated solution U sub M. And third step, we derive the 3 types of a priori estimates for the approximated solution. So this one, U sub N, in from this estimate, we can see the U sub N belongs to this class. And the second one is from this one. So we have the U prime sub M is in this class. And third estimate follows the U double dot sub of 0 is in L2 functions. They are obtained from the standard ways, including integration by parts, and Korn's inequality, and Grunwald's inequality, and also we use the compatibility condition number 2, etc. What I'd like to emphasize here is the friction force G can be depend on the both of X and T. As a fourth step, we extract a weakly convergent subsequence based on the a priori estimate presented in step 3. A subsequence of U sub M can be extracted, denoted by the same symbol for simplicity, and there exists some U sub epsilon in W2 infinity of L0 to H intersection of this one, such that this convergence holds as M tends to infinity. Then by compactness arguments, U sub epsilon solves the number 4, this one, and therefore number 3. And next, we passage the limit epsilon goes to 0. Then a similar way to before, there exists some U in this class satisfying these conditions as epsilon tends to 0. And note here that phi epsilon of this one tends to just the absolute value of the double brackets of U tangential part of U prime in C. And the Lebesgue differentiation theorem, one sees that this U solves the variation inequality number 1. So we can conclude the existence of the solution of the problem E prime. As a final step, to complete the proof, we show the uniqueness of the solution. It's just easy way. Let U sub 1 and U sub 2 be the two solutions for the number 1. Then we have this inequality. So which is immediately yielding U sub 1 equal U sub 2 in H for almost everywhere T. So we complete the proof of the main theorem. So to close my talk, I'll mention our future works. So for dynamic contact problems with friction, elastic problem is very difficult because even contact problems are unsolvable for elastodynamic equations. Today, I showed you a result for only frictional problem without contact conditions. So as the next step, we consider problem taking into account of non-penetration condition, just like a contact conditions. This is just the next problem. But in fact, it's already done by generalizing these conditions. And in today's problem, frictional force G is given. So it's so-called Tresca friction conditions. So we want to consider the Coulomb type frictions. So this is unknown function sigma sub n. So, but this is very difficult. So it remains an open problem. So maybe this is very challenging the problem. And suddenly, so we want to apply the friction problem in mathematics to the fault rupture in earthquakes. So in the seismology, there are a lot of models of the friction, like slip rate dependent friction. This means the friction constant is dependent on the rupture velocity. So we want to analyze this type of frictional laws in mathematics. And also I have interest in inverse problems to determine the rupture velocity and so on. So maybe that's all. So thank you for your attention.
Thank you, Professor Itou. Questions or comments?
I have a question.
Yes.
In your talk, you consider isotropic homogeneous elastic body. Is it possible to consider non-homogeneous, non-isotropic elastic body?
Maybe it's possible, I think, but of course it's very complicated. But yeah, maybe it's not so considerable problem. So,
but can you show the place where the difficulty appears if you consider non-homogeneous anisotropic body? Where is the difficulty appear?
But in anisotropic case, we have also we can have the same estimates.
Probably it should be. It should be.
Should be, yeah.
Okay, thank you.
Okay. Any other question or comment? Thank you once again, Professor Hiromichi Itou.
Thank you very much
for this very interesting talk of elastic problems. Those applications of differential equations are always pretty cool. Now, also in the frame of the special workshop of the 70th anniversary of Professor Alexander Khludnev, we have the pleasure of share with Professor and researcher Lazarev Nurgen Petrovich. He is researcher at the Northeastern Federal University in Yakutsk, if I am not mistaken. And he will talk about the equilibrium of a thermoelastic plate with non-penetration